The principle of moments plays a very important role in your day-to-day life. In many devices you use, like the common balance, taps, etc. To understand the principle of moments better, let us first understand the concept of resultant force of parallel forces. For this, consider a body AB, which is a uniform rod. Also consider parallel forces P is equal to 10 Newton and Q is equal to 4 Newton, which are in the same direction acting on AB simultaneously at P and Q respectively. Forces P and Q are called like parallel forces, as their lines of action are parallel and they are acting in the same direction. Let us now calculate the resultant of the two parallel forces. Here, the magnitude of the resultant is R equal to the sum of the magnitudes of P and Q, denoted by P and Q respectively. Thus, the magnitude of resultant R equal to 14 Newton. The resultant R has the same direction as that of P and Q. The resultant acts as a point C between P and Q such that P into AC is equal to Q into BC. Now let us reverse the direction of force Q. The magnitude of the resultant is R equal to the difference of the magnitudes of P and Q, which is equal to P minus Q. Then, R is equal to 6 Newton and has the same direction as that of P, that is larger than the two forces. R acts at a point C outside AB on the side of the greater force such that P into AC is equal to Q into BC. Now, consider force P and Q of equal magnitude and opposite in direction acting at A and B on the body AB lying in the XY plane. Forces P and Q on the body rotate the body in the same sense. Hence, forces P and Q form a couple. Therefore, the action of a couple is to rotate a body. Equal and opposite forces, whose lines of action are different and which act simultaneously on a body, constitute a couple. It is important to note that the resultant of P and Q on AB is 0, and hence the body will not have any translatory motion. The turning effect of a couple is called its moment. It is equal to the product of one of the forces and the perpendicular distance between the forces. When a body rotates due to a couple and reaches a position where forces P and Q act along the same line, its moment becomes 0. There are many situations in your day-to-day life where a couple comes into action. Let us look at some of them. While opening a tap, a bottle cap, a pen cap, a doorknob, turning a screw using a screwdriver, turning the screw of a earring, operating the steering wheel of a car or the helm of a ship, winding the spring of a clock or a toy, and finally, when churning curd with a manual churner. You can experience the action of a couple. Consider a scale OP, which is hinged at O. Now, a force F is applied at P. Due to the force F acting on the scale, it starts rotating about point O. Now, we say that there is a moment due to the force. The turning effect of a force on a body about a point is called the moment of the force about that point. The moment of the force is also referred as the torque acting on the body, and its magnitude is equal to the product of the magnitude of force F and the perpendicular distance between the point about which the body rotates and the line of action of the force. Here, the moment of the force is equal to F into OP, and the scale rotates about point O. If a line is drawn through O perpendicular to the plane of rotation and the scale is rotating around this line, then this line is referred to as the axis of rotation. The SI unit for the moment of force is Newton meter. There are many situations in your day-to-day life where you come across the application of a moment of a force. When you pull a door holding its handle, the moment of the force rotates the door about the hinges. Similarly, when you push a window, it rotates about the hinges. A grinder in rural homes can be rotated by applying a force, which produces a moment about the point of rotation. A cycle wheel can be rotated about its center by applying a tangential force. Now let us understand the principle of moments. When a body is in equilibrium under the action of forces in a plane, the algebraic sum of all the moments about a point is 0. That is, the sum of the clockwise moments about that point will be equal to the sum of the anti-clockwise moments about that point. Also, the algebraic sum of the upward forces will be equal to the algebraic sum of the downward forces. Consider a uniform scale, AB, which is supported about its center of gravity G, and is acted upon by a number of coplanar, parallel forces F1, F2, F3, F4, and F5, perpendicular to the rod at distances D1, D2, D3, D4, and D5 respectively from the center of the scale. Forces F1, F2, and F3 produce anti-clockwise moments about point O, and these moments are taken positive by convention. Forces F4 and F5 produce clockwise moments about point O, and these moments are taken negative by convention. According to the principle of moments, the algebraic sum of the moments taken about point G must be equal to 0. Applying the principle of moments here, you get plus F1d1 plus F2d2 plus F3d3 minus F4d4 minus F5d5 is equal to 0. Or plus F1d1 plus F2d2 plus F3d3 is equal to F4d4 plus F5d5. Now let us conduct an experiment to verify the principle of moments. A uniform meter scale is balanced at its midpoint O on a wedge, and unequal weights W1 and W2 are hung from it, W1 to the left of O and W2 to the right of O. Now the positions of W1 and W2 are adjusted until the scale becomes horizontal. When the scale is horizontal, D1 and D2 are the distances of W1 and W2, respectively, from O. Now, W1 into D1 gives the anti-clockwise moment, and W2 into D2 the clockwise moment about point O. Now the values of the variables W1, W2, D1 and D2 are tabulated. If W1 into D1 equals W2 into D2, then the principle of moments is said to be verified. The experiment can be performed for various sets of W1 and W2. In each case, the principle of moments is verified. The experiment can be also conducted by hanging a weight W1 on one side of O at distance D1 from O, and a spring balance on the other side at some position on the scale. Let the distance of the spring balance in this position be D2. The spring balance is pulled until the scale is horizontal. Note the reading of the spring balance when the scale is horizontal. Let this be W2. Now, W2 is the force that helps balance the scale, and its moment about O is W2 into D2, which is clockwise moment. W1 into D1 is the moment of W1 about point O. Now, the values of the variables W1, W2, D1 and D2 are tabulated. If W1 into D1 equals W2 into D2, then the principle of moments is said to be verified. Now let us see how we can measure the weight of an object using this arrangement. A known weight, W1, is hung from the scale on one side of O. The object whose weight, W2, is to be determined is hung from the scale on the other side of O. The positions of the known weight and the object are adjusted until the scale is in the horizontal position. Now, note distance D1 of the known weight and distance D2 of the object from O. Then, according to the principle of moments, W1 into D1 equals W2 into D2. Weight of object W2 is equal to W1 into D1 by D2. By substituting the values of known weight W1, D1 and D2 in the relation, we can obtain the weight of the object W2. A physical balance works on the principle of moments. If W1 is the weight of the object in the left pan and W2 is the weight of the weighing stone in the right pan of a balance, and the beam of the balance is horizontal, then, according to the principle of moments, we should have W1 into D1 equal to W2 into D2. Here, D1 and D2 are the distances of the left and right pans, respectively, from the center of the beam. However, as D1 is equal to D2, we have W1 equal to W2. That is, the weight of the object in the left pan is equal to the weight of the weighing stone. Now let us discuss the Roman steelyard, which is another balance whose working is based on the principle of moments. The Roman steelyard consists of a beam, AB, pivoted at C. The whole steelyard can be supported from a large hook. Beam AB is horizontal when no load is attached at A, and the rider S is at O on the calibrated beam. O is the position of zero reading on the calibrated beam. In this position, two forces are acting on the beam. The weight W of the beam itself acting downwards at its center of gravity G, and the weight S of the rider at O also acting downwards. The fulcrum F of the system is located at C. Taking the moments of W and S about fulcrum C, we get S into CO is equal to W into CG. Let this be equation 1. Now a load of unknown weight W1 is attached to the hook at A. The adjustable rider S is moved towards B to a position X on beam AB to balance the load. The beam is now horizontal again. In this position, taking the moments of the weights W, W1 and S about fulcrum C again, we get S into CX is equal to W into CG plus W1 into CA. Let this be equation 2. Subtracting equation 1 from 2, we get S into CX minus CO is equal to W1 into CA. Let this be equation 3. Here, Cx minus Co is equal to Ox, which is equal to the distance x of the rider from the zero reading of the beam. So equation 3 becomes S into x is equal to W1 into Ca. Let this be equation 4. Therefore, we have W1 is equal to S into x by Ca. Let this be equation 5. In equation 5, knowing the values of S, X and Ca, we can calculate W1, the weight of the load. Weight W1 is directly proportional to the distance x of the rider from O. The calibrated scale marked on the beam can enable us to read the weight directly.